Good day. So, today we continue the lecture on simple stresses in machine elements, and this week is the lecture 6. Now, in the bending stress, we consider a beam subjected to pure bending. Now, which you can see by this figure. So, this is a beam which has got a prismatic cross section and it is under a bending moment M. Please note that this bending moment is equal in both the sides, which signifies that the beam is under a pure bending. What we call is a pure bending, means there is no change in bending moment from this section to this section. Now, under the action of such pure bending onto a beam element, what we can see that the top layer will be under compression, the bottom layer will be under tension. So, obviously, somewhere in between there will be a layer where there will be neither there will be any tension or compression. Now, this particular axis is called neutral axis. Some other thing what we can also consider, that in this case of pure bending, the cross section of the beam is symmetric, has got an axial symmetry, and again the assumption is that after such bending, the plane section, or means the cross section remains plane even after the beam has undergone a bending. Now, I will show you with the help of one small rubber model that how a bending takes place. Now, this is one simple rubber which you can consider to be a beam segment, and my two hands, one on this side and another on this side, is approximately applying a uniform bending moment, equal bending moment rather, to be more precise, at the two ends. So, if I apply a bending like that, you can see that what we have just discussed earlier, that the top fiber is under compression, so that the length of the beam segment, this particular segment, is getting an compression, and the beam segment at the bottom side is getting extended, that means this is under tension. So, obviously, what here has been picturized by neutral axis N A is actually what we call as a neutral axis. That means, at the line along that neutral axis there is neither any tension nor any compression. So, this is precisely the model of a beam under a pure bending. Next, we go back to the text once again. So, what we have seen is that a beam which is coming out to be under bending means this particular beam, what we have considered in the earlier figure, was something like this. This what we call as a neutral axis, this we call as a neutral axis, and this is acted upon by an pure bending. That means, bending moment at both the sections are coming out to be the same. Now, under the action of this bending moment, as we have just seen that earlier, that we can have some idea is something like this. Once again, we draw it in a bend shape mode. let me redraw this once again in a little clarified manner. This is the beam, this is the line, say segment. Now, this is the line after it has come across and bending. Now, this was the section got bent in the similar manner, and this what we call as a neutral axis. Now, we understand that here if we consider the original one, then this is the original one and which got twisted to this line as it is shown in the figure. So, obviously, if from this one at any distance y, please note that we consider this as a positive direction of y, at any direction y, if this was the length of the original fiber and that we consider as dx, then this is the increment what we have obtained at this condition. Now, when it has come to this bend shape, let us consider that this particular line is having a radius of curvature, we consider that as to be rho, and this angle we consider to be say a small angle d theta. So, obviously, what is the length of this particular elongation? So, if we consider suppose this was a, now it has come down to a dash, then the length of this particular segment we as increment is a dash, and what is the original length? The original length was the thing what we consider as a line, this length a, suppose a double prime. So, a double prime was the original length, and this what we can consider as a strain in x direction. So, this we can consider as an epsilon x. So, if the strain of this particular fiber at this distance can be even written. What is this one? With respect to this angle, this is y d theta divided by this we can consider as a dx. Again, one thing we can see that this y d theta is an increment, and what is the relationship between d theta and dx? Once again we can see that this particular one, when we consider this length dx, then immediately we can see that this rho whatever we are considering the distance, this rho d theta was nothing but dx, because this was the original length. So, once again we can consider this one as rho d theta equals to this is dx. So, obviously, if we substitute, then we can see that this d theta by dx, if we substitute, it comes out to be equals to y by rho. Now, this gives us a simple idea that epsilon x, or the strain of the fiber, is coming out to be equals to y by rho. So, if we now let us consider again that epsilon x we found out to be equals to y by rho. So, what is a stress? Sigma equals to E into epsilon x, that is equals to coming out to be E y by rho. So, we can see the stress is varying for a given bending moment E and y constant. So, the stress varies with the distance y from the neutral axis. Now, let us consider the cross section. Let us take at any arbitrary cross section, and only thing we have to remember that this is the neutral axis, if we consider this to be the neutral axis, and this what we are talking about, that it is a line of symmetry and this section will be symmetric about the both the sides. So, if we consider a small elemental area somewhere at a distance of y from the neutral axis, and if this area we consider to be dA, then what is the total force acting onto this particular one? The total force acting onto this dA area. So, we know the small force, and this force we are considering to be dN is nothing but sigma into dA. So, this comes out to be sigma equals to sigma into dA. So, if it is sigma into dA, then what is the total normal force acting onto this elemental area, this entire cross section? That is coming out to be sigma into dA integrated over the area A. Now, if we substitute that value of the sigma as we have obtained from the earlier expression, this expression, from this expression, if we consider that expression 1, from here if we consider this particular one, then what we can see is that n comes out to be equals to integral over area E rho into y dA. Now, this expression can be again simplified to the form E by rho, because this is constant we can bring it out of the integral, this is integral y dA. Now, can we understand that what should be the value of normal force acting onto the cross section? The value of normal force acting onto this cross section is precisely equals to 0, because there is no normal force acting onto the cross section, it was a pure bending. So, thereby if this the normal force acting onto the cross section is 0, then from this expression E and rho cannot be equal to 0. So, what we find out that integral y dA must be equals to 0. This obviously integration over the A. Now, can we look this expression from our this particular expression from our earlier knowledge of properties of area? So, in this particular case what we can consider is that integral y dA equals to 0 signifies nothing but the centroidal distance is 0. Where from the centroidal distance was measured? The centroidal distance was measured from this neutral axis. Thereby, we get an very important conclusion from this concept or this understanding is that what we can get is that once the centroidal axis coincides with the neutral axis. So, what this idea tells us is that for a given cross section of beam under bending, the always the neutral axis is the same as the particular centroidal neutral axis, the same as the centroidal axis of the cross section. Now, this is one very important conclusion and one should keep a note of this one. Now, again we consider the same figure what we have drawn earlier and consider an area. over that one dA. What are the force over this one? We found out the force. Force is dA multiplied by the stress is the force. So, delta F, if we consider a small normal force, then it was sigma into dA is the force. What is the moment? So, dm amount of moment generated, because this is at a distance y. So, this becomes equals to sigma dA into y. So, what is the total moment? What is generated over the cross sectional area m, that is integral over the area A sigma dA into y. So, if we substitute the values of sigma dA into y, then what we get? Sigma was coming out to be what? It was coming out to be E integral over the area A E y by rho. So, this comes out to be a square term, this multiplied into dA. So, that comes out to be integral over the area. So, y square dA, and I missed this one. So, this should be E by rho. So, what we get? The total moment, once again you can recognize this term integration over the area y square dA. This is nothing but the second moment of area about this neutral axis. Okay. So, what we get? We get an important item from this one, that is m equals to E I by rho. So, if we find out E I by rho, then what we are getting? This particular one, again if we substitute the value of E y, we found out this E y was nothing but what was the value? This E y, if we replace it, then we got earlier that sigma was nothing but E y by rho. So, E by sigma by y comes out to be E by rho. So, that means sigma by y into I comes out to be the expression, and so we get sigma equals to m y by I. So, this one comes out to be a beautiful relationship, is widely used in the bending of beams. So, this one if we consider our result, so we have got a very important relationship, that is called sigma equals to m y by, you can identify my by I, a very common English word, what we can see over here. Now, if we just go one step ahead, then this comes out to be m divided by I by y, and this comes out to be a important relationship which is called m by z. Now, what is this z called? The z called as a section modulus. Okay, this is called a section modulus. This is a very important parameter in the bending of beam. You can see the stress level at any point can be reduced if we go on increasing the section modulus. How we can increase the section modulus? You can see I by y. So, obviously, section modulus can be increased in such a way, an example can be given over here. So, let me show you how it can be done. Suppose here is a body, a normal rectangle. So, what we can consider this mass. Suppose this mass, this one and this one, we just by any means we can arbitrarily place at a distance. Okay. Then what you are getting? Then we are getting the more away from the neutral axis. So, thereby I just referred this as a neutral axis. So, once we go back more and more away from the neutral axis, we thereby increasing the I. Of course, y also getting increased, but does not matter, the overall value of I by I will increase. So, what we understand that if we keep our materials much apart from the neutral axis, then we get a better value, I mean the higher value of section modulus Z. Better value I mean to say is that it will be better for the stress levels. So, that means the stresses in the machine members will decrease. So, one of the very common say is that I section is one of the very common type of section is being used when we consider the bending of beam. So, this gives you idea that how you concentrate or how, I mean how you can calculate on the values of bending stresses when the beam is under pure bending. But the question is that if AM is varying, what happens? If N is varying, then of course the bending won't, we call the bending won't be pure. Then will under this particular case the sigma equals to m y by I is valid? Then the answer is yes. How we say answer is yes? Because from experiments, that means from, if we call experiments, from experiments it has been seen that what? It has been seen that the equation sigma equals to my by I is quite valid. So, what we understand is that the way, even if the bending stresses are generated on the beam due to varying bending moment is also acceptable, and acceptable in the sense that the sigma equals to mi by I equation is quite valid. Now, in that regard, what one can see is that this gives rise to an situation called shear stress in beam. What we are considering? That pure bending, no change in bending moment along the length, then bending moment changes along the length. So, that what we are telling that at this section it is M1 and that this particular section it is coming out to be M2. So, if we consider a small elemental segment or small elemental section A, B, C, D, then what we can see that it is, if this is M, then if onto the other side C, D, it will be coming out to be M plus D M. A small change, what it is coming out to be in the bending moment along the length. What happens if such situation comes into picture? As I have just told you, that is called the shear stress in bending, means due to this unequal bending a shear stresses will be generated along the fiber or along this particular direction of the length in the beam segment. Let us see how it happens. So, what we can see is that a small elemental length, as we have seen in the figure. So, this small elemental length we have taken up, and what we have drawn the figure like this. Now, what we will be doing? Then let us consider some section line over here at a distance y. Okay, at a distance y1, not y, sorry, y, we can consider this to be at a segment say y1. Then we select this portion of the segment. So, what was this one? This was along the length, it was x, and this is the y, this is the y direction, as we have seen, this is an x y direction, and this is the segment what is coming onto the picture. So, if we analyze this particular one, then what we can see, this is the section what we have shown there. Now, let us take up that small section. We can understand that we have taken the bottom portion of the section. So, this side will be under the tension, this side will be also under the tension, and what is the stress? If we consider this as sigma, then this side of the stress will be sigma plus d sigma. Of course, this the neutral axis of the x direction was coming somewhere here. So, and this distance what we consider to be as a distance y1. So, we understand then this becomes a total segment. So, if we look from the cross sectional side of view, if we consider a cross section something like this, cross section something like this, and consider suppose at a line at any distance, let me draw a little realistic this figure. Okay, this was the cross section we consider because it is matching, this is the cross section. So this is your inner view of cross section, means this one if you view from this side, the total cross section, this is your z then, and this is coming out to be your y. So, at this location, anywhere at this location, means this is the line, this is coming over here. So, at any location we take a small elemental area at a distance y, and this line is at a distance y1, and let us consider this line to be extreme fiber to be considered to be say C1. Now, we will be interested to find out what is the total normal force acting onto this area, say A, B, C, D, onto this area, this entire area A, B, C, D, what is the total normal force. So, if we consider this face, suppose we consider this face as PQ and this side as RS, then what is the force onto this particular PQ side? PQ side onto this small elemental area, it is coming out to be sigma into dA. This is the force acting onto this area. So, if it is sigma into dA, then what we will be getting? Sigma into dA. So, total force will be what? The total force, that means force on side PQ will be integral over the area dA. So, it will be more, it will be better that this integration limit we can now put it, that will be from y1 to C1 integral sigma dA comes out to be the total force onto the PA. So, if we consider these values of this integral sigma dA, then what it is coming out to be? Sigma equals to my by I, we have learned just now. So, y1 by C1 equals to my by I into dA. So, we get this one on the PQ. So, onto this face F, what is this one? FRS, we get a similar situation, that is y1 to C1, we get sigma plus d sigma into dA. So, if we substitute d sigma into dA, so it will be coming out to be the same thing as y1 to C1. What will be the situation? M plus dm, because this d sigma is created due to the change in bending moment and other things remaining the same as y dm. So, this is a force onto this segment, this is a force onto this side. Now, of course, the sigma onto this side is less than sigma plus d sigma on the other side. So, there will be an imbalance in the force. So, to balance the force, so we understand a force in this direction and the interface should work, and that we are designating as an tau. So, this tau is a what we call is a shear stress that is created along the line of the beam. Now, you can very easily understand that what we are generating, that if sigma and sigma on the both sides were equal, that means if the beam were subjected to pure bending, no shear stress is present. But the moment there is a change in bending moment from this section to this section, so thereby we are trying to find out, we can see that there is a stress that is coming out into picture, and that what we called as the shear stress. So, if we have written these two expression, let us go to the next page. So, what we can find out that this one just to have an, this was a force F PQ, this was a side PQ, this was a force, this was shear stress tau, and this was RS. So, this is force RS. So, what we can write down, that force, and this tau cannot be in the stress level. So, tau is this length. What was the length? We considered this length to be a dx, and into dx, and we consider B. What is B? B is the width of the cross section. So, B is coming out to be the width of the cross section. So, we can very well write the force balance. So, the force balance gives us one important thing, that F PQ plus tau dx into B minus F RS equals to 0. So, if we can find out that tau dx by B will be coming out to be F RS minus F PQ. What it stands now? We have found out from the earlier integrals that it will be coming out what? It is something like that, dm by I into y dA, and this limit was from y1 to c1. So, what we find, that this particular expression can be simplified once again, that this particular expression we can think of once again equals to what? dm by I integral y1 to c1 y dA. So, what is this particular term y dA, integral y1 to c1? That means, if we look into the cross section, then this was the area where we have found out the force. This was y1, this was c1. So, this is nothing, but if we consider somewhere a centroid, then this is the length distance from the neutral axis of the beam section. So, what is this? Was the beam width B. So, we can find out that this shaded area or this one is the area for which we have computed this y1 c1 equals to integral dA. So, this one we can consider, that if we multiply by this one, say y bar, then what we can say, this is first moment of area about neutral axis, first moment of area about neutral axis. So, it is customary to write down this as dm by y into q. So, therefore, what we find out that the magnitude of shear stress what we can computing is dm by dx into q by IB. What is dm by dx? We know this is nothing but the shear force VQ divided by IB. So, what is this one? This is the shear force. So, what we get? We get an important relationship that tau equals to VQ by IB. Now, what you can understand from this one is that at a given section the V remains essentially the same, and this is an I, this is the B width, this is same. So, that this Q isn't varying. What I mean the Q isn't varying? So, the Q could be determined for this one, Q could be determined for this entire zone. Similarly, Q could be determined for entire this zone. Okay. So, depending upon the three situations, one over here, another over here, another over here, this Q value will be go on changing. So, looking at that expression, I need not compute once again, you can understand the variation of this shear stress tau will be something like this, which will be 0 here because the Q is coming out to be 0, and which will be maximum because of this was is a neutral axis where the Q comes out to be maximum and we are getting a shear stress maximum. So, what we conclude from this particular analysis is that shear stress in beam, this tau will be arising whenever we are getting what? Whenever we are getting the variation in bending moment. If there is no variation, then what we get? No tau in the beam. So, this is a very important conclusion that the shear stress comes out to be due to the variation in bending moment along the length of the beam. Now, what we can see is that this particular study of the shear stress in bending we have just concluded, and so what we can see the next one to be discussed is a torsional shear stress that is arising due to the application of torque onto the machine element. Now, when a torque is applied to a member, then it causes a shear stress. So, what we have to find out? We have to find out the relationship between the torque and shear stress developed in a circular member. Why circular member? Because in this particular one it is there is nothing that why we should only learn circular member, it could be also the circular member, but now we are considering it is for the circular member where the torque and the shear stress relationship we are going to determine. So, non-circular cross sections also can be equally modeled for this sort of relationship, but now we are only considering the circular member which are very common in the machine elements like shafts, bolts, nuts, etc., which are very commonly could be under a torsional shear stress. Now, the basic assumption of this analysis is the material is homogeneous and isotropic. a plane section perpendicular to the axis of the circular member remains plane even after twisting, that is there is no wrapping takes place and the material obey the Hooke's law. What we understand is something like this. You can see a circular member, it is subjected to a torque, and this one we can see this we will be considering this torque is, I think we should put this one is coming out to be in this direction. Okay. So, in this case what we can do is that this is the torque direction, just one second, this is the torque direction. So, this is one way it is the torque and another way it is getting the torque, this is not to be considered, this is the, so this way we are getting this particular torque. So, we can see that a face will be changing from this place to this place, that means the plane section remains plane, means with respect to, suppose there are several planes, circular planes. So, this plane will, if we consider from this side to this side, so this plane will rotate with respect to this plane just as in rigid body, just like an, just a simple sliding of this one take place, and there is no distortion, means the diameter of the shaft remains same, just like an plane it rotates. But you know that what happens, that in case of non-circular shafts we can encounter such type of wrappings might be coming into picture when it is a non-circular cross section. Nevertheless, we are concentrating our calculations based on to the non-circular sections, circular sections, sorry, circular sections only. So, we can go to this particular page once again to derive these relationships. So, what I can just assume is something like this. Suppose we consider this vertical line to be x, that means this is the direction of x along the plane. This is just for a simplicity of explaining, we are considering a torque T, means with respect to this one what we are having, let me write it clearly, this is a torque T. So, this particular shaft will be acted upon by the torque T in this manner. So, if we consider a section somewhere here, if we consider a section Mn, M dash, N dash, then what we can see, that we will just bring out the section to have a little exploded view. So, if it is having this exploded view, then what we can see, exploded view of this one. Just please note that this is a circular member. So, obviously, we will be getting something like this, a section, something, shall we just let me draw it little neatly, we get it something like this. Anyway, after all, I am trying to put to a sketch, not a very good drawing, but conceptually I think it should be okay. Now, this is a element, you understand that we are taking something like this, just a piece of cake, as if taken out, a piece of cake has been taken out, all right. This should be this is a dotted inside line. So, something like this. Now, if we consider this line say A, B, C, D, what is this one? Let us represent this element not in terms of T, but in terms of the shear stresses. So, obviously, shear stress direction tau, referring back to the free body diagram. See, here is very important, you draw a free body diagram. From here, if you make a cut onto this section, torque will be in the opposite direction, in this direction. So, at this cut onto the other side means if I give an exaggerated view of the cut, means you understand what I mean to say is something like this, that you consider this is a cut. So, free body diagram will show what decision torque. So, obviously, torque on this face in this direction, so other face it is this direction, so on so forth. So, obviously, the direction of shear stress is in this direction, direction of shear stress is in this direction, direction of shear stress is in this direction, and what we consider the direction of shear stress is this direction. We have learned earlier that the shear stresses will always appear in pairs. So, that this element is always in equilibrium. Now, by virtue of this one with respect to means this one means this application of this pure shear, because there are no other forces acting. We can imagine that with respect, if we keep this one fixed, then this particular face goes on something like this. This face just shifts to this face with respect to this one. Okay. So, let me make this figure little clear, just erasing out other aspects what we have already discussed. So, this I am just erasing. Now, let us concentrate only onto this element, only onto this element we are considering. Okay. So, what we can see is that if we join this line, this line, this line, and let us see that this C has shifted to C dash. Then what we know? This angle we know gamma. What is this one? The shearing strain. And what is this line? This line has shifted. So, if we consider an angle, suppose we consider this angle to be delta phi, and this length of this element we are considering as dx. Okay. Now, what we can understand that this particular length C dash. So, how we define this one? The shearing strain gamma, then this gamma. We have learnt earlier, of course, about the shearing strain gamma. So, this shearing strain gamma will be this particular distance by this particular distance. Now, what is the radius of this particular circular member? Let us consider the radius of the circular member to be r. So, gamma is perpendicular by base, and that gives you what? It is r d phi by AC is dx. Now, what is seen that this what we call this angle of twist means with respect to this face, how much this face is rotating due by virtue of applying this torsion T. Now, this particular d phi is proportional to dx, means what do you mean by this? And d phi is proportional to d. So, what we can find, d phi by dx is a constant, this is a constant term. So, we can see that we write down this as an r theta. Now, so obviously, this theta is a constant and it is being referred to as angle of twist per unit length. This is called the angle of twist per unit length. So, having gone through this one, let us again choose another page. So, this shearing stress we have come down as R into theta. So, what is the shear stress tau? Shear stress tau equals to, coming out to be equals to G into R into theta. So, if it is coming out to be G into R into theta, so this we are getting as the relationship. What is G? This is a shear modulus of elasticity, that what we have learned earlier. Now, that means what we can see, that if this is constant, the shear stress variation is linear, or in other words we can see in a figure wise that something, if we consider the piece of cake sort of idea, then this is your shear stress variation coming like this. Okay. So, this variation is coming like this. This is a linear variation. Now, instead of R, means instead of taking the element onto this face R, we can have this element somewhere at an radius rho, somewhere in radius rho, means if we look at the circular cross section, this was the thing. Okay. Now, we consider some other regular, say rho, at a distance rho. Then also this tau is 0 theta is valid. Okay. This is a generalized way, if we can write it down. Then what happens? Then if we see from the top view, then we get this point, that rho, this is your rho, and this area what we are considering is dA. So, can we not find out the net external torque T? Torque T is how much? First we shear stress into elemental area is the shear force multiplied by rho is the torsion, tau into dA is the force multiplied by the rho is the distance. So, if we integrate over the area A, then what we get? This is the expression. Now, what is the tau? We find out this A, that is G theta rho square dA. Now, this comes out to be G theta integral what? Over the area A rho square dA. Can you recognize this term, this particular term? Yes, you can recognize, I suppose. So, we get G theta integral over area rho square dA. It is nothing but polar moment of inertia, polar moment of inertia. Okay. So, that means what we get? This gives you the idea of the torque. Now, again if we look back from the earlier expression of G theta, means we got this tau equals to G R theta. So, at the end or at the extreme radius, what we can find out? G theta can be replaced by what? G theta can be replaced by tau by R into I P. So, thereby shear stress tau equals to T R by I P. This is a very important relationship. And if we go back once again to a fresh page, then important relationship is tau equals to T R by I P. This is a very important relationship we use too often in machine element design. Now, again a question comes, what is the total angle of twist phi? So, this equals to theta multiplied by L. What is theta? We have found out theta again from the same expression. This particular one is tau equals to g r theta. So, we can find out this theta and then replace it by the tau. So, what we can get? This replacement will give us theta equals to T L by G into I P. You got the point? That means you have, I am not going to evaluate it, you can just simply substitute this value of theta from here, and tau by G R comes out to be of this particular formula. So, we get phi equals to T L by G J. So, most widely used two torsional formulas are like this: shear stress tau equals to T R by I P and phi equals to T L by G I P. What is this L? I think I did not mention. This is the length of the member. So, here today we have learned about what? We have learned about the bending stresses, we have learned about the shear stress due to bending. This is number 1, this is number 2, and we have learned about, I have written tau. Anyway, this represents the shear stress, torsional shear stress. So, these are very important stresses that develops in the machine element, and in the further classes we will find that in addition to these main categories of stresses that we have learned in the earlier class about the axial stresses and the direct shear stresses, today we have learned about bending stresses, shear stresses due to bending and torsional shear stresses, and something more relevant we will be learning in the next classes. Thank you.